So guys, up to now, just recap what we did with this starting with image acquisition. Okay, and said that it's a continuous image, so we sample it, quantize it, and then move towards the spatial domain later on. And here on the right side, we did the first transform the image and perform the image enhancement and image restoration. So there are some advantages if you move towards the transform domain. Okay, so now we will just go towards another topic which is called the extension and threshold. Okay, so if we direct the edge and did the threshold, we can also segment the images. Why segmentation is needed? Because in some of the application, I can segment them in like to identify various objects. Okay, object detection. Now also we have like face detection of different people, and also let's say number plate detection of the car. So there are like a lot of application of segmentation in general can be done in two ways. One is edge-based detection, where I'm just trying to find the edges in the image. Okay, if I locate the edges, like here, what I did, okay, I just find the edges. Okay, so if I somehow locate the edges, I can segment this object from the image. Okay, so this is the edges. I detect edges, and after that, I separate this object. But however, there's some limitation with the edge-based detection. So what we can do is, for example, here, if I do the edge-based detection, there's a lot of edges inside. So if I do the same thing, like that's a lot of edges, which should not be there. So the other way is to do the similarity, and I select the portions and try to find what are the similar components in that picture. For example, these, if I select the segments from here, this will be very similar as compared to the background. Okay, so the background parts will be similar to the background, and the foreground, which is the object, will be similar to the foreground. So I can separate it. Let's say, for example, one of the simple way is to plot the histogram. So I will say one histogram of the background and the other histogram of the foreground. Like the two histograms will be point separated, so I can separate them. Okay. So mostly here we do edge detection, and the second part here we do thresholding based on some criteria. Okay, and did we before? We did it right in Charleston. What we did? We were detecting the edges. We did the first order derivative. I think second order derivative we saw Laplacian, we saw other derivatives as well. The at for edge detection we will start with the same thing. So there will be some repetition, and then we go towards some of the advanced methods of the things that we do. Okay, more than that we covered previously. So starting from again the very basic thing that we discussed this. So definitely I will not go into any detail. And this we discussed is this we have either have first order derivative and second order derivative. And the first order derivative has these properties. Okay, so it's a zero in the area of the constant intensity. We discussed this. Also non-zero in the onset of the intensity of the step when we have the step jump on the ramp. Okay, so that will be non-zero. Similarly, if we are on the ramp, still it's non-zero. So there is one of the disadvantages that on the ramps where there's no edge, okay, still it is non-zero. So if I take the second derivative, it remove this drawback of the first order, and it is zero along the ramps. However, there are some other advantages of the second order derivative. If I take the first order derivative, it's resulting in a thinner edges as compared to the second order. And the second thing is the second order derivative also gives some indication if we go from light to dark. If I go from light to dark, this is the edge, right? Or if I go from dark to light. Okay, so there is some indication in sign. Okay, and we will see some of them here. So this is what the first order and second order derivatives. First order we have seen three kinds. One is the forward, backward, and the center, right? Second order is this one that we have seen before. Okay, so then we can have even third order, fourth order as well. Okay, so from there we get it from we have a Taylor series. Okay, and some of the functions. Okay, so if we try to manipulate it, I will get all these equations from the Taylor series. But definitely this is not our topic. And similarly, I'm not interested in third and fourth order, so this does not need the information. Okay, we will stick to the second order like before. Okay, this is an example also we have saw before. We have like here, if I take a line, I get this thing, right? So I want to detect the edges. Like this is the edge, this is the edge, this is the edge, and this is the edge. If I do the first order derivative, I still somehow locate these edges, but these are, let's say here, this is a thicker as compared to second order, right? So the second order is more edgier, plus it's also, for example, you have a ramp here, so I'm expecting it to be a zero, right? Because there's no edge here. So here it's not non-zero. Here, second order, it's zero. Okay. So some of the advantages, but still we have some first order filters as well, second order derivatives. Okay, still it's not necessary that I'm excluding it. Right? Don't ignore the ramp, because our target is to get the edges. So the ramp, inside the ramp is not edge. Okay, the edge is only here at the beginning of the end. So second derivative is giving the right indication. But the first order derivative is not giving zero. So it means that this is somehow not good. Okay. However, as we go in detail, you will understand more. So one way, let's say you want to detect a point in an image. What can be the application of detecting a point in an image? Okay, so I want to detect this point. Okay, so what's the application? One is a medical image. In that medical image, you have some tumor or something. That is appear as a point. Okay, so point detection is necessary as important in, let's say, in medical image processing. Let's say you are scanning some electronic components or some in a factory and there's some defect. So we are interested in point detection because point is just a sharp transfer, right? So one way is to use the Laplacian transformation that we have seen there. That's a Laplacian filter that we have seen there before. This equation we can write in this fashion, and if we want filter, is the filter we use this filter to convert with the what? With the image. So let's say here we have something here. Okay, and I want to detect it. So I will apply the here. I just convolve the Laplacian filter with the image. I get something, and you can see it's been prominent but not that prominent. So what I can do, because I want to detect this, so I will just what I will do threshold. Okay, because this is, you see, the lighter point as compared to the whole image. The lighter point means the height, and the background is low. So I will just have a threshold, and I get that point. Again, this is application already I discussed with you. That was segmentation. Okay, anything else? So this is the thresholding I have to use in order to get this thing. Okay. Okay. This is clear. Okay. Then definitely if you are detecting the point, then we detect the line. Make sure that all these filters previously we did for sharpening. Okay. Our purpose was sharp. But in between you are detecting the edges. Detect the edges, then you add to the image, this was one of the filter, and we try to sharpen. But we did not look in that filter from the perspective of the edge detection. Okay. So now line detection. So let's say you have some electronic chip, something, and you want to detect it. Now here is why we want to detect these lines, because there's, let's say, some fault or something, and something is not appearing here, or something is broken, or some defect is there. Okay. So if I apply the edge filter, I will be able to detect that thing. Okay. So let's apply on this. Let's apply the Laplacian transformation. You get this image again. Although they detected the edges, but it's not clear. So one way is to find the absolute value. Okay. The other way is to just find the maximum value. So in both cases, you will get some edges. Here, like there are different ways to improve the session. Either you can positive values, good values. This is what we have to show. Okay. However, not only this, but if we rotate the filter, let's say I have this filter, right? But this filter is what is this doing, sharpening or what? Edging. Because whenever you see the negative, it means that you are doing some, you are detecting edges. Okay. Eliminating, not eliminating. It will be eliminated when you have a constant intensity. Then it's eliminated. See, because you see, if you have constant region of same intensity, -1 and 2, so it means this will be 0. Okay, so it will have a value when you have an edge. Otherwise, it will not have it. Okay, so now based on this filter, if I want to detect specific lines in a horizontal, I mean as a horizontal or vertical or diagonal, I can do that. Okay, what do you mean by this? Let's say okay, now this type of filters, whenever you see some positive, I mean this is actually the reference filter, and this is, we call it the vertical. Vertical means this is x-axis. You remember that this was the axis, right? Okay, okay, and this was y, right? So this is my reference. Okay, so this is vertical, this is my reference. If I rotate it by plus 45 degree, what I will get? This thing, okay? Come back on and back on. Yeah, yeah, okay. It's become like this, right? And if I do -45, this becomes like this. Yes or no? Okay, and similarly, if horizontal, it will be like this one. This is clear. My reference is the vertical one, in which how to find which one is vertical. We have to find this type of pattern, positive and all the same. This means this is vertical, and this is axis is y-axis. So if I want to rotate, I will rotate like this. And then if you want to go very systematic, you can use the rotation transformation that we discussed in some of our first and second classes. Okay, we use cos, the sine, j sine, and try to find it. Okay. Now, what's the purpose of this rotation? If I use this one, this will give me the horizontal lines more prominent than others. If I use vertical on this one, it will give me the vertical lines more prominent than others. So the way I want to find edges, I can do that. Let's say if I apply this filter, which is 45 degree on this, so I will get this type of image. And if I just zoom in this part, I can see that the edges on the 45 degrees more prominent than others. Similarly, if I just saw this one, this is like this. So this is the positive values only. Okay, from here I get this, and you can see that huh? Just take the positive values. So if that is the case, you can see that still there are other edges as well, but these are more prominent because our filter was 45 degree as compared to the vertical. Okay. After that, in order to isolate these lines from others, what I did, I just did some thresholding, and you can see that there are some lines after. If you're sure that okay, I just want diagonal, let's say, because this is an example of, let's say, an electronic board or some electronic chip. So let's say I'm interested in just this one. I'm trying to find some defect in that. So I will just try. If I'm sure, I will apply this. If I'm not sure, I will just apply in every direction. Try to find it. So now, what can be the type of edges that we can have, that we can detect, and that we can have? Okay. So either it will be a sharp transition from black to white, or light to dark and dark to white. Similarly, you can have a slow transition, like a slow ramp, and this is again we call it roof edge, like going sharply back. But the important thing is, we will discuss this later on, that the images are not very clear always. We have a noise. Okay. So since we have a noise, you will not get very symmetric or very nicely placed edges. Okay. So what we need to do is, we have the image, we first need to smooth it a bit in order to reduce the noise and then apply the edge detection. So in that case, mostly the edges are like this. Which makes sense, right? If we smooth it, this will be like this, not like edgy like this. Okay, I will discuss this one. Fine. Just yeah, this picture in this location, we have this type of edge. Okay, this ramp. Then we can have this one, or we can have this one here. Okay, so it's not really clear here, but if you zoom in, you will try to find out if these edges are here. So yes, 3. Yeah, so these are the most common type of edges that we are interested in. Okay. What we discussed is that the first derivative produces a thicker edge profile as compared to the second order derivative, and which is clear. Let's say I just want to plot this line, I will get this lamp. Okay, so if I take first order, I get this thing which is thicker than this one, right? This is more edge here. Okay, whereas these second derivative, why I have one? Just take the second derivative and find. Okay, yeah. So I mean, in terms of imaging, that means that we have an edge, either going for dark to light or light to dark. That's sharp, maybe sharp, black and white sharp, no smooth. No, we don't need smooth. We need the edge. Okay, and the good thing about the second derivative is, for example, we are going from here to here, right? So if you are going from here to here, means that from low to high, and this is see what is this high? If I'm going from here to here, from light to dark, okay, so I'm going from here to here, and you see what is the edge? So if the second derivative is multiplication from where we are lying, okay, and also it has some, okay, so it always produces two values for every edge in an image, second derivative, and also the zero crossing. What is zero crossing? If I connect these two, I get the zero crossing here. This zero crossing. Zero crossing is actually can be used as locating the centers of the thick edge. Okay, so this is the edge. The center can be located here, where if I join the two edges. Okay, but the problem is the noise. I'm discussing very ideal case where there is no noise in the image, which is this one. Okay, so I have an edge, this first order, second order. But if I just put some noise, the first is with zero noise, zero variance noise. And we have 0.1 variance noise, which with a small noise, what I get, although the noise is not clear here. You can see here, not quite clear. However, if I do the first derivative, I get this thing. The second derivative still we get but with the noise. Okay. Similarly, if I increase the noise with one, okay, there's noise appearing here, and the first order and second order is like completely almost not visible. Okay. Similarly, if I increase the intensity, even you cannot see the edges. Okay. So this is a problem, right? Okay. So this is again, if I take the first order derivative, I get this thing. Okay, for the noise. So what's the solution? Smooth it, right? Okay, so let's do this. And this is the same thing. Why we don't get the edges is because the noise made the corresponding of the neighbor's pixels very random, not similar. Okay, so that's the reason we did not get the edges. And the stronger the noise, the stronger the response, means that the stronger the noise, the stronger will be this response. Okay, the more ideal will be the response, and we cannot. So what should be done? We can just smooth the image, and then do this. So let's say this is 1D case. We have this edge with the noise. Okay, if I apply Gaussian filter in 1D, it will smooth it, right? And after smooth, I get this thing. How to do smoothing? Convolution, just convolve this with this. Okay, simple. And after that, if I apply the first order derivative, I get the edge. The edge is again the very thicker, so I can take the maximum of that to find this is the box. Okay. Now, how many steps we did the smoothing? Then we take the filter, we did the smoothing, and then we derivative. Okay, can we reduce the steps? The derivative of the filter. Why I can take the derivative of the filter first and then come on with the image. Can I do that? Why I can do that? It means that I actually, what you're saying is that I should just change this operation here and convolution before. Can I do that? Why? Why derivative? Yes. Why derivative is the linear operation? The question is that I can change that. Okay, you also said that I can change it. Yes, I can change it. But my question is that if I change it, these should be a linear operation, right? But why derivative is a linear operation? Yes. Okay, what is derivative? If I take this differentiation, if I differentiate, then we are discussing this. What is derivative? First order derivative on the edges. Difference, right? Yes. A difference. How we find that difference? We convolve the signal or the image with a conv, right? So basically, derivative is also a convolution operation, right? So it means that I have convolution here and I have a convolution here. So we have two convolution is associated. Okay, so I can change the operation. That's the reason of doing this. Huh? So I can write this and this. Differentiation is convolution and convolution is associated. Differentiation something like yeah, that's the next step. But if I want to find the difference, let's say forward difference, let's say go back, check that. Let's see the first start out with this one. So what is derivative? You see this? So what is this? This is convolution. If I want to apply this, this filter on the image, it means that I am convolving the image with what? With the 1 minus 1. So basically, this thing is actually convolution. Okay. Okay. So this is done. Okay. So for the edge detection, if you remember, there were two main things that we were doing. One is that we were taking different type of filters, particular filters like first order derivative or the second order derivative, and based on that, we have Sobel operator or some other. You'll see that. Okay. Roboter operator or the laptop, and then how they are combined. So we have two things. One is the type of filter. Either we have the first order derivative, second order derivative, and how these are combined. Let's say you have one axis and y axis. So either I should add them in that loop enough, or I should take the magnitude. Okay. So these are two things that makes a filter. Okay, that we can use for edge detection. So one of the simple edge detection method was the taking the gradient. Okay, like derivative in x and derivative in y axis. Okay, and then either I take the magnitude, or I can take the absolute and add. Why I'm taking this? Because this is computationally expensive. So I can just take this and it will serve the same purpose as this. Okay, I'll get the same information. Okay. Now, if I just divide the gradient along y-axis by x-axis and take the angle, okay, what information it will give me? This will give me the direction on which the edge is there. Okay, why this direction is important? Because if I know the direction of edge, maybe because of life, I may get some direction good, some edge is good, some edge is not. I can connect that. I know that this is the direction of the edge. Okay, so if I take this angle, okay, if I take the angle, this one, this gives me the angle of this gradient vector. Okay, this is the gradient vector, and this is the angle. So this is the angle alpha. Okay, but however, this is the gradient angle. The edge angle is perpendicular to the gradient angle. Okay, which is this one. Okay, so alpha minus 90 give me the edge. Okay, this is the angle of the gradient that I'm calculating, and the edge direction is perpendicular to the that gradient. Guess why? Because it makes sense. Let's say you have two. This is black, and this is white. Okay, so let's say only you have this thing. So it means you have only what? Y-axis, right? Y-axis. So what will be the gradient? Gradient vector will be like this. The direction will be like this. Will be 0. But what will be the edge will be here. So this is what perpendicular to the. Okay, makes sense. Okay. Again, this again two operators forward, backward. Okay, so x and y, and in terms of vectors, I can write this. So basically, I am convolving an image with this to get the gradient along x and y. This is why I already did it. So we are just connecting the more plots, and we are going more advanced. Okay, fine. And then we also discussed some other operators, which are Roberts, Hewitt, and Sobel. Okay, and I think we discussed this thing, right? All of them. So based on the filter, orientation, and the components or the coefficient within the filters we defined. Okay, so this is like gy and gx, and in order to combine them, I can take the absolute and add. Fine. One of the we did not discuss very deep into Sobel operator, and let's go a bit deep at how it's being made. Okay, we just discussed that. Okay, we are taking the differences, and this is somehow the differentiation or way of differentiating, and that's why it's giving me the edge. But if you go a bit deep into Sobel operators or the operators, I can see that this has better noise suppression characteristics as compared to others. And the question is why? Okay, why? Because if I just Sobel kernel is made basically to Gaussian vector with the central differentiation and convolve that, okay, and get this kernel. So what's the benefit? We discussed it that we have to first smooth the image and that is the indication. So what he did, he was not right, is what he did the first order central derivative. So this is the filter. So that, like in this filter, you are gaining the both benefits, edge detection and noise suppression. Okay, so that's why it's better. It has better suppression properties as compared to other operators. And I think this example we already did this before. Right? Remember that? Okay. So anyhow, this is easy. You have the image, and this is gx, gy. You can convolve with first gx, then gy, and then either take the magnitude or the approximate it with the absolute and addition. Fine. And this is the Robert operator. Again, this is the same similar example that we discussed before, but this is an image. We just did the zero padding on one side because the Robert operator is 2 by 2. Okay, and we just find gx, gy, find the magnitude, and similarly, as we discussed before, that orientation of the filter also is important to detect the edges at the specific angle that we want. So the pivot and Sobel, if I want to rotate it, also this will detect the diagonal edges as compared to the horizontal and vertical. So this is what it is. And how to find that this is diagonal? You have to find the similar elements along the one axis that will give you how much orientation it is as compared to the vertical one. Okay, so this whole orientation is as compared to the this one. Okay, because this is our reference. Vertical one is the reference. Okay, so if you want to rotate 45 or minus 45. Okay, just another example, just to show that how orientation of the filter detect the edges. Let's say you have high intensity and a low intensity in image, or low and high. So if I convolve with this image, which is a vertical, and I know that here the edge is vertical. Okay, so if I just convolve it, you can see that there is some edge here, the indication of edges, right? Similarly, if I just go from low to high, again the edge is negative. So it means that this type of filter also gives you the indication that we are going from high to low or low to high. Then there's another operator, 8 directions, okay, corresponding to the 8 direction in north, northwest, west, southwest, south, and similarly. So like you have the compass. Okay, so in that compass you have all these directions. So we have 1, 2, 3, 4, 5, 6, 7, 8 directions. Okay. So what is the reference? The reference will be the vertical one, which is south. Okay. Fine. So this is the reference, and then they are rotated. But anyhow, if you want, we'll take one go. Yeah. Just rotate 1 by 45, 45. Fine. Yes, because 45, right? If you want this from here, 45, then 45, 45, 45. Like, and you see, this is my reference. Vertical. Okay. Okay. So what he has done now? For example, if you have 8 kernels, so what? Okay. Yeah. So what he did is actually he convolves one by one with all of them, and then take the maximum at each point. Okay. Why? Because one, let's say one of Yeah, separately, and then you have to find the maximum on all these 8 values. Why? Because if let's say one of them is good in finding one edge, the other finding another edge. Okay, so if I take the maximum, so maximum will give me the all the edges that are good. So let's say if I convolve with this one, okay, if this may give one edge, okay, good, other edge may not be very prominent. Okay, but if I convolve with this one, it may give the edge that was not prominent, be prominently given by this one. So if I take the maximum of both, I get the best edges for both of them. Okay, and I have an example as well. Okay, and again, what will be the direction of the edge? It will be again the maximum on the particular edge or the particular pixel, which our filter is giving me the maximum. The direction of edge will be like on that direction. Let's say north give me the maximum as compared to others, then the edge direction is on the north side. Yeah, discrete variable. Because we cannot do all of that. Yeah. So this is again, we have all these 8 filters, and this mathematically I convolve image with all of these 8, and for each pixel, you have to pick the maximum from these 8. Of course, yes, but it's better as well. Okay, so let's compare. Let's say you have Sobel operator. This is gx, this is gy, this is magnitude. Okay, and you can see that edges are like not very prominent as compared to the constant region. Although it's somehow given, but still that edges are not prominent. I need just edges. Okay, but there are some other stuff coming. Like they have kind of edges. They have, but I need the major edges. No, these edges of this house only. Okay, now it depends. Sometimes yes, you might be interested in that, but here I'm not interested in smaller edges. So here, what we did, instead of just finding the edges, I first smooth the image. If I smooth the image, okay, this will remove the small edges like this one. Okay, so this is gx, this is gy, and this is m. This is much better as compared to previous. It's over. So it's over. But only thing is that this image is, I just smooth it and then apply the same. Okay, and then not only this, I went another step and also did some thresholding in order to remove all completely the small details and just check the edges. So it's not a smooth image. We did the thresholding. You see, this is there's some gaps. If we similarly for smoothing, it's much better than this one. But if I see that, okay, this is a numerical example of the same thing. You have a Sobel operator apply on the image. If I apply Sobel operator, I just convolve with gx, gy, okay, and then after that I normalize the image to get this is the result. After that, I just apply the threshold, which is 1.2 times the average of this one. Okay, the last thing is the Kirsch compass. So if you see same image, I apply one filter, one of the filter, 8 filter here, and another one of the 8 filter here. So if you see here you see, this is more prominent, but here it's not prominent, right? Here it is prominent, not prominent, and here it's prominent. If I take the maximum, what I will get? Less edges. Okay, so this is what it is. Okay, then there's another very interesting method. And if you remember Sobel, what he did, he basically take the Gaussian, convolve it, which order derivative first order, right? So Marhardert is again another scholar. What he did, he Gaussian with second order.